All right, last time I had talked about, I started with calcitonin, which is the hormone that brings high serum levels, so serum levels that are above 10.4 deciliters, milligrams per deciliter down, so it tones the calcium level down in your serum. And then I went to the actually far more common occurrence where your calcium levels are too low, which is under the control of two hormones, primarily parathyroid hormone, which I ended with talking about last time, and then calcitriol, or calcitriol. I pronounce it calcitriol. So that's what we're going to pick up with today. And the story of calcitriol is, bottom line, it also raises plasma calcium levels like parathyroid hormone. How does it do it? Well, first of all, we have to talk about how we get it, where it comes from. And calcitriol is a fat-soluble hormone that is derived originally from cholesterol, and specifically 7-dehydrocholesterol. It's a variety of an unsaturated variety of cholesterol that's found in the skin, helps your skin to remain supple. And then when your skin is exposed to UV radiation, narrowband UV, a very tight wavelength of UV light, helps to convert that 7-DHC to vitamin D, vitamin D3, in fact, cholecalciferol. Vitamin D3 then circulates in the bloodstream, and as it passes through the liver, it gets converted to calcidiol. Calcidiol, you can see with the addition of that hydroxyl group on that six-membered ring on the tail of it there. And then calcidiol circulates through the kidneys, where under the influence of parathyroid hormone, if parathyroid hormone is present in the bloodstream, then the kidneys will convert calcidiol to the active form of calcitriol or calcitriol. And, oh geez, sorry about that. Get this thing just right. Here we go. And what does that do? Well, the primary function of calcitriol or calcitriol is to increase nutritional absorption of calcium at the gut, and phosphate as well. All right. In conjunction with the activity of parathyroid hormone at bone on the osteoclasts and osteoblasts, and on the reduced excretion of calcium at the kidney, we're going to raise plasma concentrations of calcium. Where do we get vitamin D3? Well, the bulk of it actually comes from sunlight. The vast majority of our vitamin D, cholecalciferol, is derived from exposure to sunlight. And I said narrowband, it's in the UVB range, around 200 to 300, or 290 to 320 nanometers, about 300 nanometer wavelength light. But there are a lot of other excellent sources. So I showed you the chemical structure, not because I wanted you to be able to draw the chemical structure, but simply so that you would know that it is, in fact, a fat-soluble vitamin, right? It's a fat-soluble molecule, and it's found in a lot of foods that have fat. So cod liver oil is probably your highest source out there of vitamin D3. So a teaspoon of it is over 100% of what you need in a day. I know cod liver oil is probably not everybody's favorite out there, but it can be found in a lot of other cold water oily fish. right? So sardines, salmon, mackerel, even tuna has a little bit of it in it. Milk does have some vitamin D3 if it has been fortified with vitamin D, and we'll talk about that in a bit. You can find it again. So caviar, who doesn't love caviar for breakfast? Has a small amount, and there is about 10% of your daily need in vitamin D3 in an egg. You'd have to eat almost a dozen eggs to get everything you needed in a day. However, those of you who like mushrooms would have to eat 100 cups of them in a day to get your vitamin D. But everybody has their own dietary preferences. All right. So what happens if we don't get enough vitamin D? And this is a real question because they say, so the statistic is something like 14% of young Americans are actually vitamin D deficient. There is a large number of people that are vitamin D deficient, even to this day in the United States, particularly in a place like Maine, where that number is certainly higher. And that deficiency may be subclinical, where it just is leading to a chronic bone density issue, or it may be clinical, and the clinical manifestation is what we call rickets. So rickets was first identified by Cyrannus of Ephesus in the 1st century AD. However, it resisted proper treatment for ages and ages. This guy, Kurt Hulczynski, in North America and in Europe, in the northern climes where people are not exposed to as much sunlight, particularly in the Midwest, which is, I'm a Midwesterner. Anyone else? No one else in here? Anyone? Hey, yeah, you guys remember what it's like living in the Midwest growing up? Gray all day, every day. It's pretty gray today. This would be a very typical Midwestern winter day, not exposed to a lot of sunlight in the winter. Well, this guy, Kurt Hulczynski, determined that if he exposed children with rickets to a UV lamp that had the right wavelength of light, that their rickets resolved. So this was prior to the discovery of rickets. Oh, so I have the statistic, 3% of children in northern U.S., but the other statistic I had was 14% are somehow vitamin D deficient subclinically, and then 3% actually present clinical rickets in this country. So it's quite a bit. That's like 1 in 30, 1 in 35 kids. That's a lot. All right. Enter this guy in the bottom middle here, Elmer McCollum. So he's a pretty interesting character. I'm going a little bit. I know you guys didn't have this slide in your in the PowerPoints that I put up yesterday. I just threw it up there. I couldn't help myself. Elmer McCollum's a pretty interesting character. He was maybe the self-proclaimed or somehow dubbed America's doctor, America's nutritionist, back in the early part of the 20th century. So he discovered a whole slew of vitamins. He discovered vitamin A, several others, vitamin C, but he discovered vitamin D in 1922. He initially was at Wisconsin, up in Madison, and while he was there, he kind of got on the dairy industry's payroll, where the dairy so it turns out that it's because vitamin D is a fat-soluble vitamin. It's really easy to get it into solution in milk. Milk is kind of an ideal vehicle. Why is it an ideal vehicle? There's a lot of fat in it. Yes, absolutely. Why else? There's one other reason that vitamin D is a really great vehicle for milk is a great vehicle for vitamin D. Everybody drinks milk. That actually wasn't the case that wasn't the case before Elmer McCollum. Indeed, almost everybody drinks it now, and it's thanks to this story that I'm telling you. What did I say vitamin D did? Or actually not vitamin D, but calcitriol, the downstream product. What does it do? What's the whole topic here? Yeah. Where? In the gut. All right. So to absorb calcium, there's got to be in the gut. There has to be some calcium in the gut. Turns out milk is a really high source of calcium, right? So it's a pretty intuitive pair, right? It's a pretty intuitive pair. And after that was discovered, then all of a sudden they started pumping vitamin D into the milk supply, and then happy milk delivery men like this guy suddenly sprouted up everywhere, and milk became not just a beverage of the lucky farmer who got up early to milk Bessie, but a daily staple in households across America. And this is when the mass marketing program of the dairy industry, the Dairy Council in the United States, took hold. So here we see them appealing to your patriotism. Vitamin-rich milk and nourishing foods, other foods have, lots of other foods have calcium, are the foundation for a strong America. Indeed. So, yeah, milk consumption in the United States doubled within a decade. It doubled within a decade. That's quite a bit of milk. That's a windfall for the Dairy Association. There's more to this story, actually. Elmer McCollum really got the laurels for all this. He was a bit of had some other kind of quacky ideas. But I said up there that he discovered vitamin D. It wasn't actually him. It was this woman that was working at his lab. But I'll leave that there. It'll pique your curiosity. You can go research that on your own. Let's get back to calcium homeostasis. All right, so this kind of synthesizes or integrates everything in the last several slides in calcium homeostasis. So let's start in the middle, all right? And let's raise calcium levels in the blood above our reference range of about 10 milligrams per deciliter. This is going to stimulate the thyroid to release calcitonin to help tone down the calcium levels. Calcitonin is going to act on the kidneys and the bones. It's going to, in so doing, reduce the calcium resorption by the kidneys, so we're going to urinate out more calcium, and we're going to deposit more, store more calcium in the bones, thus lowering the blood calcium levels, the serum levels of calcium. On the other hand, if the level of calcium begins to drop, the beginning of the process here is the stimulation of the parathyroid gland. Parathyroid gland, in response to the lowered calcium levels, begins to produce parathyroid hormone, which is going to have the opposite effect on the kidneys and bones. So at the bones, it's going to stimulate the release of calcium by doing what? What did I say? What cells are going to be affected in the bones if we're releasing calcium? What were the names of the players, even if you can't remember what they did? There was osteoblasts and osteoclasts. Osteoblasts build bone, and osteoclasts corrode bone, right? So if we're going to be releasing calcium, which one's going to be more active? The one that's dissolving the bone or building the bone? Dissolving the bone. So the corroding, the osteoclasts get upregulated and the blasts get downregulated. And then at the kidneys, we're going to be resorbing more of the calcium, but and less will be passing into being excreted into the urine. But also, the kidneys will be stimulated under the influence of parathyroid hormone to convert calcidiol to calcitriol. All right. So once calcitriol gets put into the bloodstream, this is the active form of vitamin D. This is going to have its effect on the intestines, and it's going to increase the intestinal absorption of calcium. All right, bringing the blood levels back up to the reference range that the body likes. Make sense? Pretty straightforward. This is how we maintain the appropriate levels of calcium in the body. Okay. So, your serum level of calcium can be indicative of various disease states, particularly when it is cross-referenced with the serum level of parathyroid hormone. Okay, so that's what we're looking at here. We're looking at the cross-reference of parathyroid hormone and calcium in the serum. All right, and this blue box in the middle is the normal range. The normal range. So we can see along the x-axis, that's the reference range I was talking about 9 point whatever, about 9 milligrams per deciliter, up to a little above 10.4 milligrams per deciliter of calcium. And then I have a log scale for the parathyroid hormone, right? Because it can be there can be a wide dynamic range of parathyroid hormone. So, and then there are these 4 regions of different color. So if you have high parathyroid hormone but lower calcium levels, that can be indicative of renal failure. Your kidneys are not able to resorb as much calcium as they normally would, even though there is a high level of parathyroid hormone telling the kidneys to pull it back in. There's some kind of problem with your kidneys, kidney failure. However, if there is abnormally high calcium and abnormally high parathyroid hormone, then you can have hyperparathyroidism. That means your parathyroid gland is dysfunctional and is not responding to the calcium cue in the blood, and it's just pumping out more and more parathyroid hormone, driving your calcium levels way, way up. Yes, ma'am. Omarosa.
Why isn't it
because you don't really see people with that combination of conditions. I mean, it's with that combination of lab panels. I mean, each of these disorders is going to have characteristics that are not going to be divided neatly, right? Yeah. I mean, your body wasn't thinking about coordinating with different diseases to make the diagram look well. It's just the way those organs work. Yeah. And then on the other hand, hypoparathyroidism is where your parathyroid gland is not responding properly to the cues, perhaps, or maybe it's just has some other dysfunction and is not able to produce parathyroid hormone. So you have lower levels of parathyroid hormone, and because of that, your calcium levels have dropped off. All right, and then lastly is the hypercalcemia associated with some form of cancer. So a number of types of cancer are often associated with elevated levels of calcium. And the parathyroid hormone is working properly, right? We've turned down the parathyroid hormone, but nonetheless, there is still a deluge of calcium in the blood because of some type of cancer. All right. So these are the type of diagnostics that you can derive just by cross-referencing the parathyroid hormone and the calcium levels in your blood. Does this make sense? Yeah, pretty straightforward. Osteoporosis. So I'll give you a little bit of pathology here. So osteoporosis is a problem. It's a real problem. And in fact, by the time this class is mostly women. There are only 3 men in this class, which means there are 17 women. By the time the 17 women in this class are ready for retirement, at least 3. At least 3 or 4 of you, 3.5 of you, are going to be suffer from osteoporosis of some sort, and that number is going to dramatically increase after that. So osteoporosis is responsible for about 9 million fractures annually worldwide, and that number is probably a little low because that's a 2016 number. It cost the United States $28 billion in 2016. That's a lot of money, folks. That's a huge amount of money. It's a huge amount of money. If we had $28 billion infused directly into preventative medicine, we'd have a significantly improved health care infrastructure in this country. So it gets bad rapidly after the age of about 65, all right, after about 60. Why? What do you think's going on? What do you think? Can anyone guess? I said it was a problem particularly with women, and particularly of women after about the age of 60. Okay, great. Exactly which hormone? Take a guess, yeah. Estrogen, thanks. Why aren't older women making more estrogen? Indeed it is. Indeed it is. I am looking for one word. Yeah, menopause, thank you. Yeah. So women older than about 55 or 60 begin to go through menopause. And that's when their estrogen levels drop off a cliff. Estrogen, we're not going to go through the complex way in which estrogen affects osteoclasts and blasts in your bones, but it does. So this is going to be about 61 million women altogether in the United States by the year 2020. That's a lot. By 2020, there's only going to be 350 million people in the United States. That's about 1/6 of the U.S. population. 1 in 6 people in the United States are going to be suffering from osteoporosis. Okay, so what? Well, it leads to tremendous amounts of fractures and reduced quality of life for these people. You can see here in the bottom, this is the soft bone, the trabeculae of the bony spicules of the bone. And on the right, this is healthy, and on the left, no, other way. That's my left and right. The left is healthy, the right is not. The osteoclasts have been totally released from any kind of regulation by the estrogen. And so they just continue to dissolve bone and erode the integrity of those bones, particularly in the spine, hip, and wrist. All right. Men are not immune to this. Men also get osteoporosis. Men do have estrogenic hormones in their body that help to regulate and maintain bone density. So the estrogen essentially acts as a throttle on the osteoclasts, turning the throttle down. And once you remove that, then they speed up and rapidly dissolve the bone, and it becomes poritic. And that's what you see here on the right-hand side. So when you look closely, microscopically at these spicules of bone, you see there's these little holes, these perforations. The porosity of it goes way up, and density goes down. A person goes from a normal spine to a kyphotic spine. I'm sure many of you have grandparents or parents who may look like this. Does anyone's seen that in an older person? It's due to this problem right here. All right. So I said I wasn't going to talk about the details of it, and I'm still not. Actually, I'm not going to go through that diagram at the top. But there's a number of ways. There are a number of ways you can deal with it. There's estrogen replacement therapy, right? This slows the bone resorption. It keeps the osteoclasts in check. You can get, obviously, pharmaceutically derived estrogen that you can take. There are even crunchy people out there who save and lyophilize their placenta and then powder it and take, 20 years later, they take the pills themselves because there's a high concentration of estrogen in the placental tissue. Seems like a lot of work, but it's done. And then you can get a little bit more intense. There are various drugs, Fosamax, Actonil, and their job is to specifically kill off osteoclasts. The problem is not that you have too many osteoclasts. The problem is that they're too active. So this can lead to problems as well, right? So instead of having many moderately active osteoclasts like is healthy, you have a few super active ones, and this can lead to osteonecrosis, a very unpleasant situation. This is a side effect of it. So you can get a short-term remission of osteoporosis, but you run the risk of bone death. Osteonecrosis is bone death, not something you want. You can take daily injections of parathyroid hormone. This will also slow bone loss, but again, the problem wasn't with parathyroid hormone in the first place, was it? It was a problem with estrogen. So again, there are going to be some side effects to this that these patients don't really like. And you have to take a daily injection too. You have to be right on top of it. The best thing you can do is prevention. So, and how do you take steps to prevent it? Well, it begins right now, folks, in your time of life. For the next 25 years or so, the best thing you can do is pay attention to your lifestyle in just the way that I'm trying to encourage you to do with your daily logs. So this means be physically active. Get exercise that helps maintain long-term bone health. And eat right. There are a number of dietary choices that you can make that will lead to long-term bone health. I could spend an entire lecture talking about that, but I'm not. And the time window where you set the foundation for that is midlife. So starting right now for the next 20, 30 years until you're about my age. That's like the foundation you set in that early midlife is what's going to lead to the best outcomes as you go into menopause or into old age as men. All right, so that's that. Let's switch over to the other. Was there any questions on any of that material? I know I cut a bunch out, but felt like there's no point in rushing. Nope. Okay. Let's switch over to epithelium. This is where I wanted to be today. All right. Epithelium and connective tissue form the integument. Very simple, straightforward haiku today. Not especially poetic, but extremely informative. I please ask you to commit the spirit of that haiku, if not the exact wording, to heart. Epithelium and connective tissue form the integument. Okay, well, what does that even mean? What is epithelium and connective tissue? Well, the human body, so I guess the human community, the population of us, has sometimes a hard time getting along. We are more or less successful living as a community. Sometimes it seems like we do a poor job if you read the news too much, but we're still here. But the human body does a really great job of being a community of cells. There are 50 trillion cells of 200 different cell types. So there's about 200 different countries, 200 different nationalities on Earth, and only about 8.5 billion people on Earth. Your bodies are 50 trillion of 200 different cell types. That's staggering that they're able to get together with such comity. Well, these cell types are distributed through a variety of tissues. And what is a tissue? It's a collection of cells and cell products that perform specific and limited functions. All right? And these tissues then make up organs. We talked about tissues and organs a little bit when I talked about the hierarchy of life. We're sort of walking our way up that hierarchy right now. An organ is simply a structure that has firmly delineated boundaries or discrete boundaries that is made up of two or possibly many more types of tissues. When considering tissues, there are 4 categories that we break them up into. 4 categories of tissues. All right, there's many different types of tissues, but there's 4 categories that they're broken up into. And we're going to talk about the remainder of this week and maybe a little bit next week. 2 of them. So the 4 tissue types or categories are epithelial tissue, connective tissue, neural, and muscle tissue. So epithelial tissue is tissue that covers an exposed surface. They are like the outer layer of something. That can be the outer layer of your skin is certainly made of epithelium. But also, if you think of surfaces on your body, like if you shrink yourself down super tiny and walk over the surface of a body, well, you're walking on epithelium on your skin, but maybe let's walk up the nose and we walk all through the sinus cavities, right? The nasal cavity. That's covered in epithelium. Now we're going to walk down the pharynx into the mouth and the esophagus. That's all covered in epithelium. We're walking down through the stomach, the GI tract, all epithelium. We walk out of the other end of that tube, that which we are. And all the other surfaces, you could imagine walking up the urethra and going into the bladder, and then walking up the ureters, into the kidneys, into the distal convoluted tubules. The entire time we would be on epithelium, all right? Any of the sweat glands, the openings of the sweat glands onto the skin, we could be real tiny and walk down into the opening of a sweat gland and still, entire time, be walking on epithelium. It covers surfaces. It covers surfaces. Not just ones that you could walk to from the outside. There are other surfaces in the body that are covered with epithelium. For example, the inside of your cardiovascular system, the inside of the heart and the capillaries, etc. So any surface is going to get coated with epithelial tissue. Glands are simply specialized epithelium. Any kind of gland in the body is a specialized form of epithelial cells. Epithelial tissue is almost always found in conjunction with some kind of connective tissue. Now, connective tissue is a pretty diverse category. There's a number of types of connective tissue. What does it do? Well, connective tissue is aptly named. It connects things, fills the internal spaces. It acts as a support and a substrate to other tissues. So bone and cartilage is considered to be connective tissue. So that's a supportive connective tissue. The blood cells are considered to be a type of connective tissue. And so this is a fluid transport form of connective tissue. Adipocytes, fat cells, are a form of connective tissue, and it stores fat in them. So this is how we store energy, epithelium and connective tissue. And then the other two types of tissue are all excitable tissues. And this doesn't mean that they're particularly keen on anatomy and physiology. It means that there is a membrane dynamic that happens. And we're going to devote quite a bit of time to discussing how that works. Right? So there's a potential difference that happens across those membranes that can get excited and lead to, in the case of muscle tissue, contraction, or in the case of neural tissue, the transmission of a signal. Right? So there's the excitatory tissues, the neural and the muscle tissue, and everything else is either epithelium or connective tissue. Does that make sense? Pretty straightforward. That's the body broken down into 4 categories. All right, so here is the outline of all of that. Now, I am not probably going to go through quite everything on here in a gory detail, but I'm going to start talking in the last 10 minutes here about epithelial tissue. Epithelium is broken into 2 categories, 2 general categories. So proper epithelia, and this is the stuff that just lines surfaces, as I described, and then glandular epithelia. And glandular epithelia are cells that produce something. They're going to produce a secretion or a hormone of some type. Within proper epithelium, there's going to be three morphological distinctions, either squamous or squished epithelia, cuboidal epithelia, or columnar epithelia, and with various types within each of those categories. And then glandular epithelium, there's going to be endocrine glands, which I'm going to leave for the endocrine chapter, and exocrine glands, which I will have a quick flash through. I'm not going to go into in depth, but I'll talk about each of those things. So I'll walk my way through that outline. And then I will talk a little bit about connective tissue. But what I've decided to do with connective tissue, rather than I used to go through all of that stuff there. And I'm going to pare it back to only touch on the things that you need to know for the larger discussion of organ systems that we need to have going down the line, and leave the details for a later class for you guys. Muscle and neural tissue will have their own chapters. And then I will end by talking about the types of what are called tissue membranes. Tissue membranes. Not a plasma membrane, not the membrane of a cell, but a tissue membrane. What is a tissue membrane? There's 4 types of them. There's mucous, serous, synovial, and cutaneous membranes. And I'll talk about each of those a little bit. And it'll be very instructive, I hope. All right, so this is an outline of this unit. Let's start with epithelium. All right, so here is a typical epithelial cell, and hopefully enough of you guys have had basic cell physiology that I don't need to go into real depth pointing out all the features of the cell, but a couple things that are important. So epithelial cells have what's called a cellularity. And what I mean by that is that they form junctions. There's they adhere to one another, and when you look at them, it seems like they're divided into various cells. So Robert Hooke is the person who first coined the term. I think I showed you a picture of him at the beginning of the semester. It's because when he looked at cells of cork, the first cells that were ever identified, he thought that they looked like the cells of an abbey, where priests or monks may go to sequester themselves. Just little square rooms attached to one another in a large array. So there's a cellularity, there's this junctionality between cells. There's also a polarity. There's an up and down, top and bottom. Those terms aren't actually correct. We say apical, which typically is shown on the top of a diagram, and basolateral, which is the bottom. The basolateral surface of a epithelial cell is connected usually to connective tissue that lays beneath the layer of epithelial cell. So another thing about epithelium is because it has this cellularity, there is an avascularity to it. What does that word mean to you? What does the word avascular suggest? Yeah. Yeah, it actually means not only is it is equal, but it's non-existent. Yeah, avascular means there is no, come on. Yep, hey. Still has a fever. Not too bad, he's pretty good. Keep him over there. It means that because there's this cellularity, the cells are tightly adhered side by side, right, next to one another. And because of that, the blood vessels, the capillaries, can't penetrate those junctions between each other, right? So it's avascular. Whatever nutrients are getting into an epithelial layer are diffusing into it somehow, either from below or above, all right? Avascular. And epithelial cells are regenerative. They're mitotically active. They can divide and regenerate themselves, okay? So what does this do? It acts as a physical protection. It helps to control permeability. So because of the cellularity or the junctions that these epithelial cells have, it prevents, for example, in the lumen of your intestine, in the inside of your intestine, it prevents bacteria that may be in the gut from getting into the bloodstream, from penetrating this boundary that they create. And to get past that boundary, you have to go into the cell and actually get processed by it. The epithelia is often in close contact with the sensory receptors on the ends of neurons, sensory neurons, and so often there are specialized adaptations that can help provide sensation. And then finally, glandular epithelia are able to make specialized secretions. So walking through the cell, we have the nucleus, that's where the DNA is. We get messenger RNA that's produced there that gets exported to the endoplasmic reticulum, where this should be review for you, where we have translation to proteins by the ribosomes. Then we move up to the Golgi apparatus for what's called post-translational modification, where the proteins get clipped or decorated with carbohydrates or what have you. And then finally, these vesicles with secretory contents pinch off the Golgi apparatus and are exocytosed or released through the apical surface of the epithelium. All right, was that review for everybody there? I hope so. If it wasn't, we can talk some more at any point. But I'm going to keep going. All right. So because of the cellularity, the junctionality of epithelial cells, there's going to have to be, there are various ways that these cells come into contact with one another. And I'm going to talk about 4 categories of them. First, there is the tight junction. And the way I talk about the tight junction, it's like a Ziploc bag where you zip it closed. It's kind of like that along the apical surface of the cell that zips it to the adjacent cell. All right? So there's these tight junctions right along the plasma membrane at the apical surface of adjacent cells that keep them tightly adhered to one another. So there is, right at that apical surface, a single impermeable barrier to any kind of pathogen or other molecule that may be out there. And to pass through that surface, there would have to either be damage to the surface, or it would have to be absorbed by the cell and get processed by the cell. So that's the proteins of the tight junction. I'm going to skip gap junctions for the moment and move on to the desmosome. So when I was in high school, my high school had a shop class. Did anyone ever take shop class? Do high schools still have those? Yeah, shop class is fun. Did you ever get to use, Elizabeth, right? Your name. Did you get to use the spot welder? You use the spot welder? I don't remember your name. Did you use it before? Spot welder? Okay, so spot welder is fun. You have a couple sheets of sheet metal, and you put them together just like this, and you stick them in this machine that has two little electrodes like this. And you stick it in there, and you step on the little lever, and the electrodes come down and send a really high voltage through there. And it just goes, and then they come apart right away. And the two pieces of sheet metal have been welded together at that spot. That's what I think of when I think of a desmosome. All right, it takes two adjacent plasma membranes of neighboring epithelial cells and just adheres them right at that spot. All right, a hemidesmosome. Hemi, what does hemi mean? Half. Yeah, a hemidesmosome is just half of a desmosome, and half because it's attaching one cell, but now to the basement membrane. Both of these desmosomes, hemidesmosomes and regular desmosomes, are attached to the cytoskeletal elements, these intermediate filaments that extend out into the body of the cell. All right, we'll pick up there next time. I'll talk about gap junctions, and then we'll keep plowing through this. Are there any questions?